Alright, we're going to talk about how to factor a binomial, and it's the difference of two squares, okay? The difference of two perfect squares. So, the first thing is we have to be able to recognize it. Now, the difference of two squares means we need to have a subtraction sign. Okay, that's what difference means. Now, on both sides of the subtraction sign, we need a perfect square. Okay, so if we have that situation, and this is the general form of it, we have a perfect square to the left of the subtraction sign, a perfect square to the right. It will factor down into two binomials that are conjugates, or the binomials are the exact same thing, the square roots, except one binomial sign has a plus sign and one has a minus sign between them. So let's take a look at an example. I think it'll pan out more. So if we're looking at this and it says factor, and we're like, what kind of factor? We look for a common factor first. I do not see one. Okay. Then I say, okay, there is a minus sign, so it is the difference. Now, to the left of it, x squared is a perfect square, and 9 is a perfect square. So what we know, this will factor down to one binomial times another. The only difference is we have a plus sign in one binomial and a minus sign in another. So how do we get the first term of each binomial? We're just taking the square root of this. So the square root of x squared is x. So we go x, skip a spot, x. We have alternating terms. Now we look at this term here and we say, well, what's the square root of the second perfect square? And the square root of 9 is 3. So we plug 3 in, skip a term 3, and you have everything factored down. Now we always check to see if we can factor these binomials more. We can't. I'll give you an example of when we can in a second. But that's it. We're literally just taking the square root of both terms and plugging them into the parentheses. So let's do one more. We got a minus sign, so that's the difference. Actually, we're going to do two more. Now, 4x squared is a perfect square because if I take the square root of 4, I'm going to get 2. And if I take the square root of x squared, I'm going to get x. So our square root there is 2x. 25 is a perfect square, and we know if we take the square root of 25, we get 5. So the 2x and the 5 are going to be our terms that go into each binomial. So I'm going to write it out. I'm going to say 2x, a plus sign. The next perfect square is a 5. 2x again. Switch our plus sign to a minus sign. And our second perfect square, or I should say our second square root, and we're good. That's it. All right. So one more example using the same concept of difference of two squares, but we're going to add one twist to it. Okay? When we look here, 16 is a perfect square. We got the difference. It's a minus sign. And x to the fourth is a perfect square too. Okay? If we take the square root of x to the fourth, we're going to get x squared. Okay? And if you think about it, let's just look at a number first of all. You know, we know the square root of 25 is 5. Okay? Which means to get the number under the radical sign, if I square it, we should get the number that's underneath the radical sign. Which means x squared, if I square it, in our exponent property here is when we have exponents stacked on top of each other and we multiply them together, gets you to x to the fourth. So we have to recognize anytime we have an even exponent floating above a variable, that's always a perfect square. So when I take the square root here, I get x squared. When I take the square root of 16, we get 4. So we're going to boil that down and say, all right, so we're going to get x squared plus 4, x squared minus 4. Now, this is our first step into a larger process of factoring. When we get done factoring, we have to see if we can factor any further. It's very similar to a factor tree. If I had like the number 12, and we said that factors to 3 and 4, and said, well, 3 is a prime number, but 4 can be factored even more. So we would say, hey, 12 is really 2 times 2 times 3. That's what we're kind of doing here. When we get done factoring, we have to look at each factor and ask, can they be broken down any further? Do they fit one of our special types of binomials? Now, we don't have anything with the real numbers that's the different or the sum of two perfect squares. So we're done here. This is a prime polynomial. It's like the number 3. We can't break it down anymore. You know, if I had a quiz going on and there was a big old space for your answer, once we get that prime polynomial, in this case x squared plus 4, I'd write that on my answer page. So we're done. That's no more. But x squared minus 4 is once again the difference of two perfect squares. So that means x squared minus 4 can be broken down further. Just like our number 4, when we factor 12, can be broken down further. We follow our rule. The difference of squares tells us to take the square root of x squared. Place that in the first and second. For, the first term of both binomials. One binomial is a plus, one's a minus. The square root of 4 is 2, so our 2 goes in our second, becomes our second term of each binomial. Now we check. Does x plus 2 represent the difference of two squares? No, so we're done. That goes on our answer space. That's a prime polynomial. Does x minus 2 represent the difference of two squares? Oh, it's the difference. But x and 2 are not perfect squares, so we're done. That can't be broken down any further. So that also goes on our answer space. So here's our finalized factored version of x to the 4th minus 16. Okay. All right, may the force be with you.